In this video, we'll be looking at vectors in the rectangular coordinate system. A vector v for which the magnitude of v is equal to 1 is called the unit vector. And we know in math we use the word unit frequently when we mean per 1. The unit circle has a radius of 1. Our unit vector has a magnitude of 1. Two very useful unit vectors are defined as I equal to 1, 0 and j equal to 0, 1. Those kind of pointy looking parentheses, they're called angle brackets or vector brackets. Vector I is the unit vector whose direction is along the positive x-axis, and vector j is the unit vector whose direction is along the positive y-axis. With the unit vectors I and j, we can express any other vector, AB, in the form AI plus BJ. So when I see these angle brackets, I usually think of an ordered pair and then just say, okay, it's going to be the vector that goes from the origin to that ordered pair. Now, the vector v here, 3, 4, can be rewritten as 3i plus 4j. So if we look at the diagram here on the right, we've taken our vector I and we've multiplied it by 3. And we saw in a previous video that if you multiply a vector by a scalar, the vector just gets that scalar times longer. So now it's going 3 units instead of 1. And the same thing with the 4j. We know j is the unit vector along the y-axis, but the cool thing about vectors is that we can kind of just slide them over in the plane. So here it is right here, 4j, and our vector v is the resultant, 3i plus 4j, and this is where we're using the adding technique that's not parallelogram rule, where we put the initial side of the second vector at the terminal point of the first vector, and then our actual vector is connecting the initial point of the first vector with the terminal point of the second vector, and we get this right here. So it's just different notation. But honestly, when I see that 3, 4 in angle brackets, I think of the point 3, 4, and then just connect a vector from the origin to that point. A vector with its initial point at the origin is called a position vector. A position vector v with its endpoint at the point AB is written in the angle brackets AB, so vector v equals AB. This means that every vector in the real plane corresponds to an ordered pair of real numbers. Thus, geometrically, a vector is a directed line segment, and algebraically, it is an ordered pair. The numbers a and b are the horizontal component and vertical component, respectively, of our vector v. Representing vectors in the rectangular coordinates, vector v with an initial point, we'll call it P1, equal to x1, y1, and terminal point at P2, x2, y2, is equal to the position vector v equals x2 minus x1i plus y2 minus y1j. Okay, so basically what's happening here is the first two vectors we just looked at, they were position vectors because they were starting at the origin, but we could have vectors that aren't necessarily starting at the origin. So we might have this vector right here, starting at the point 1, 2 and ending at the point 3, 5. But we can make this a position vector. And basically what's happening is we're just creating a triangle. It's kind of like how we do slope, honestly. And to find this distance here, we simply subtract the two x values. So 3 minus 1, this gives us 2 here on the bottom. And then we do the same thing along the side. To get this distance here, we simply subtract the y values. So our vector could be rewritten as v equals 2I plus 3j. Because as I mentioned before, vectors in a plane, you can kind of just pick up and move wherever is convenient for you. And convenient for us is having that initial point right on the origin. So that's all this is saying. All you need to do is subtract your x values to get your a, subtract your y values to get your b when you want to write your vector in this form. So let's talk about the algebraic interpretation of vectors. So let's consider the Cartesian plane here. The positive angle between the x-axis and a position vector is called the direction angle of the vector. So this right here is our direction angle. The magnitude and direction of a vector are related to its horizontal and vertical components. The magnitude or length of our vector u equal to AB is given by u, the magnitude of u equals the square root of a squared plus b squared. And this is just Pythagorean theorem. Right, here's our side A, here's our side B. Use the diagonal, we're just doing Pythagorean theorem. Also, the direction angle satisfies tangent equals b over a. So we've created a right triangle here in our diagram, and we're just using SOHCAHTOA. Tangent is equal to opposite over adjacent, so that's where they get the tangent of theta equals b divided by a. So let's talk about properties of the magnitude of a vector. If u is a vector and if k is a scalar, then we have these properties. First off, the magnitude of any vector has to be greater than or equal to 0. And that makes sense. We're talking about the length of the vector, and we don't talk about length in terms of negative numbers. The only time that the magnitude of a vector is 0 only happens when the vector itself is the 0 vector. Property 3 says it's true that the magnitude of a vector and its opposite vector are equal. And number 4 says if we want the magnitude of a vector that's been multiplied by the scalar, we can take the absolute value of the scalar and then multiply it by the magnitude of the vector. So these properties here really just follow all the rules for absolute value. These are all our absolute value properties here. So I know in this context, we're talking about the magnitude of a vector, but linking it to something we already know, it's all the same rules as we have for absolute value. So let's find the magnitude and direction angle for some vectors u. Our first vector is -7, 4. So to find the magnitude, this is our a and this is our b. So this is going to be the square root of -7 squared plus 24 squared. Square root of 49 plus 576. Square root of 625, which is a perfect. The magnitude of our vector is 25. Next, to find our direction angle, we're using the fact that tangent of theta is equal to b over a. So tangent of theta is equal to 24 over -7, making theta equal to tan inverse of this fraction, 24 over -7. Plugging this into our calculator, making sure you're in degree mode, we get negative 73.74. Recall that our calculator only gives us an answer based on our definition of inverse tangent, and inverse tangent is only defined in quadrants 1 and 4 from negative pi over 2 to pi over 2, or in this case, negative 90 to 90 degrees. So that's why we got this angle, but check out our point from the very beginning. This is saying that our AB, that's negative 724, so that actually puts us in the second quadrant. And the angle that our calculator gave us is over here in the fourth quadrant. So we need to get from the fourth quadrant over to the second quadrant, remembering that tangent has a period of pi, or 180 degrees. All we need to do here is add 180 degrees to get to quadrant 2. So our direction angle, our theta, ends up being 106.26 degrees. Let's try another one. This time our vector u is 8 square root of 2, comma, negative 8 square root of 2. Well, let's start with our magnitude. It's going to be the square root of 8 square root of 2 squared plus negative 8 square root of 2 squared. Since the operation is multiplication between our 8 and our square root, make sure that you're squaring both. So that ends up being 64 times 2, which is 128. And we get that a second time. Squaring negative 8 is going to give us a positive 64. Times 2 is another 128. Adds together to be 256. There's another nice perfect. Our magnitude is 16. Now we're ready to find our direction angle using the fact that tangent of theta is equal to b over a. That means tangent of theta is negative 8 square root of 2 over 8 square root of 2. That simplifies down to negative 1. So let's think about where tangent is negative 1. Tangent is either 1 or negative 1 when we have a 45-degree reference angle. Since tangent is negative, that means that the x and y value have to be opposite signs. So that puts us in either quadrant 2 or 4. So let's take a look at the ordered pair that goes with this vector. We have a positive x value and a negative y value, so we're down here in quadrant 4 with a 45-degree reference angle. So that means that theta is 315 degrees.